Thanks a lot.
Okay.
Okay.
So we are in live.
We're live. Okay. Well, hello everybody, people from YouTube. Okay, so we might start as well by answering the following question. Okay, let's see. I think I couldn't connect the dots. Have we simulated a system with a positive charge when we simulated the oxidized molecule? Wasn't it prohibited? Okay, sorry, I had the audio on, so I was hearing my own voice. Okay, yeah, that is a good question. Indeed, the oxidized system, of course, had a +1 charge. However, when we prepared the system there, the topology and let's say the input coordinates, what we did was to include also a chlorine anion, so that we could neutralize the whole solvation box. So in practice, we run the classical molecular dynamics simulation still with an overall neutral species, neutral system. But yeah, what was that? The noradrenaline was positive, but the overall system was neutral. That's because we put a chlorine ion there. Yeah. Yeah, of course, if you have any other questions from the previous exercise, you can ask them. Otherwise, yeah, we can go ahead. Okay, so by the way, before we start with today's exercise, which regards the computation of absorption spectra, I wanted to make a little bit of a clarification from what we did the other day. Yeah, actually, Antonio made me notice that in regard with the way we computed the Gibbs free energies. So at this point, I'm gonna share the whole screen. Here we are, and this. Okay, so here is the thing from today's lesson. But yeah, in regard with the way in which we computed these guys here, especially the Gibbs free energy, yeah, the Gibbs free energy of reduction in this case. Now, yeah, here we just computed the averages of the energies in both cases for both of the trajectories. So on the one hand, we are considering sampling, so we are implicitly taking into account like the thermal effects that could contribute to the overall Gibbs free energy, and also somehow the vibration of the system. So let's say the normal modes of vibration are accounted for via the simulation. However, the thing is here, these guys are still averages of the energies, and these need not be equal to the Gibbs free energy, or as a matter of fact, need not be equal to the free energy of the system. So this is an approximation what we're doing here, and it's I said it's a rough approximation, although it actually provides well, comparable results with respect to methodologies that do compute these guys here explicitly. What's the approximation kind of we are doing here? Well, first of all, here we are assuming that there are small variations in volume, which is our case in the simulation. So we are so instead of the Gibbs free energy, we are assuming that we're computing the so-called Helmholtz free energy, and also we are assuming that we're computing that we have small variation of the entropy. So this is the approximation that we're having here. So this is not an exact equality. As I said, we can compare this methodology with methods that do compute this difference somehow in a formally accurate way. One example is actually this has been shown by by Warshall, the same Nobel Prize. We'll go back in the day, like 1986 or so, where you can you can compute the Helmholtz free energy, well, the reduced species and the oxidized, these deltas, sorry, they should not be here, as a function of the, well, this is the probability distribution of what? The probability distribution of the vertical, let's call them vertical transition energies, in the sense that, for example, if you run one trajectory, let's say in the reduced species, so you perform your molecular dynamics simulation of the reduced species, then you compute on top of these geometries let's say on each one of those geometries obtained from the reduced trajectory, you can compute also the oxidized state. So basically, it's like a vertical transition or vertical oxidation, in the sense that you do not vary the geometry, just vary like the let's say the electron density of the system, basically. I don't want to further go into the details, but you can do that. This is actually something people do often. We also did in a paper that Jesus Lucia, PhD student of Juanjo's group, did. Worth submitting for publication. So yeah, I have also put the references on which you can get further information on that approach. So there you do compute the Helmholtz free energies. So this is where Warshall actually shows that you can express the Helmholtz free energy as a function of the probability, the density, not the probability distribution, but the density of these vertical energies. So I have also put this on the GitHub. You can download it from there if you want. These are applications of that methodology. Okay. That being said, we can now start. Well, I think there are a couple of questions. You assume the probability function is equal to the partition function. That is, this is a good point. And actually, yeah, I gotta confess that me and Juanjo have been and Jesus have been looking at the literature. Now because you find different expressions. Now the thing is, this expression that I showed here, it is that I showed in the previous slide. Can I click? So notice that oh geez, sorry, spoiler alert. Notice that this is the probability distribution of this vertical energy. So you in practice obtain this expression by starting from the definition of the Helmholtz free energy, which is the logarithm of minus kb times t times the logarithm of the partition function. So you take that definition for the oxidized and the reduced states, and you can derive this expression here. So they are not the same expression, okay? Because here it is the probability distribution of vertical energies. So this is a specific reaction coordinate, okay? But yes, but these two guys here are derived from the definition of the Helmholtz free energy in terms of the partition function. Okay, let's see. So yeah, exactly what Juanjo wrote. That is the absolute. So that the definition of the Helmholtz free energies in terms of the partition function. You take that absolute free energy for the two states and get these guys here. Okay, this is actually well shown in this paper. So in case you want to get further details in that regard, I strongly encourage you to take a look at it. It is also on the GitHub page. The slides, I mean. Okay. So now let's go to the to today's topic, which is the computation of the absorption spectrum, in our case of azobenzene. So you're already acquainted with this species here because we have played around with it on Vito's second tutorial on umbrella sampling. So in our case, we will actually take a Vito simulation, well, the simulations you performed, and we will compute the absorption spectrum from that trajectory. So what's the big deal here? First of all, as you can see, well, whenever now this is the experimental absorption spectrum of azobenzene. I took this picture from this paper here, but I think you can find it in several different places. So now the most important thing is that, well, of course, what you have here is a rather broad band. We actually call each one of these guys a band. Now, so the first band, the second band, but now we know, or if we don't know, well, I'll be a little bit vague here, but please stay with me. So each one of these guys here corresponds formally to an electronic transition. So a transition from the ground state of the system, the electron ground state, towards a certain excited state. Okay, and since we're talking about quantum mechanics here, this is a quantum mechanical world, and this means that these transitions are quantized. So when you do this jump from the ground state to a given excited state, of course, you have a delta E, an energy difference, which is a single value formally. Okay. So if we computed, let's say, the first excitation, so excitation from the ground state to the first state, of course, we would obtain a single energy. Here it is represented in nanometers, but of course, we have different energy units. So these guys here represent energy. Okay. So when you compute that single excitation, of course, you would obtain a single bar. What's going on here? We have this broad stuff. Why is this not a single bar, a vertical bar, but instead we have this broadness here? I wrote it on the PDF, but of course, if somebody knows, could you tell me what's going on here? Why do we get these broad bands here? Why don't we get just nice vertical bars, like a single point energy? Sorry, the intensity as a function of the energy as a single bar. Could somebody tell me? Could in the chat or via microphone? No. Okay. Okay. I actually see a lot of. Oh yeah. Go ahead.
Well, I think it's because of the interaction of the molecules, the bulk of the molecules, and there are several configurations that can, in the ground state, that can suffer, I don't know how to say this excitation, and gives those kind of bands.
Yeah, this is indeed the main thing, the thing we're going to tackle today. So you said the keyword. There are several configurations because, of course, now at this point, I'll jump to the next slide. But of course, the situation that I represented before, in which I said, okay, we should have a single peak for each electronic transition, regards a single configuration. And usually when we compute absorption spectra, what we do as a first approximation is to consider only one configuration, the equilibrium configuration. Okay. Now, of course, the absorption spectrum consists of the excitations from the ground state towards different excited states. I have represented just two of them, the S1 and S2, but there are many more. But the point is, if you consider only one of these guys, you have, of course, one vertical bar for the first excitation, another vertical bar for the second excitation. So formally, this would be our absorption spectrum. Of course, when we do that, we usually want to compare this with the experiment. So we also apply some kind of broadening on top of each one of these bands, of these bars. And then we have two nice bars. But remember, this broadening that we're applying here, it is non-physical, okay? This is just for comparing with the experimental data that resembles like this thing here. So for example, in our case, we would have one peak here, a second peak here. That, in case we perform the computations on top of a single geometry. Now, what Lucas, I think it was Lucas who said that we in the ground state we not only have this one geometry here, but of course we have motion, as you have already seen in the previous lesson. So yeah, sorry. So what do? We have to account for this motion in the computation of the spectrum. The reason is because the molecules are moving, but when light comes and excites all these molecules, it takes a picture of the whole system. And in this picture, we will have one molecule that is like this, and the one that is like that, and so on and so forth. So what should we do? Well, we perform sampling, right? This course is in part about sampling. So this is what we do. And once we perform sampling, to account for at least partially account for the broadening of each one of the excitations, of course, we obtain this guy here, and for each, sorry, we obtain this ensemble of configurations, and for each one of those, we have the corresponding vertical lines. And these vertical lines are those that contribute to the overall spectrum. Now, I said that, of course, I mean, we still have vertical bars here. Yeah, sorry, spoilers. We still have vertical lines here. Of course, this vibrational movement does not fully account for the broadening of the band. There are also some other factors. One of those is Heisenberg's uncertainty principle, but this goes beyond of this lecture. So we still have this guy here, which nonetheless is kind of a better reproduction of the spectrum. We can still apply some kind of broadening here to still compare it with the experiment. But notice the difference. Now we have, for each, let's say, band kind of, we have different electronic transitions that are related with different configurations. Now, formally, what we are doing here is we are accounting for the so-called bibronic transition. So each transition in practice is associated with a normal mode of motion. And they need not give you the exact same energy difference. Hence, the number of vertical bars that you see here. Okay, so that being said, we are going to do the two things here. So the first thing is we're going to compute the absorption spectrum for, we're not going to do it for the equilibrium geometry. We're going to do it for a random geometry, and we're going to see what we obtain. And afterwards, we're going to do the same thing for the whole ensemble of geometries under consideration. I think it finished up here. Yeah. Okay. So at this point, we can, well, I'm going to stop sharing this screen. I'm going to show another one where we will start doing the exercise. Okay. Again, if there are any questions, don't hesitate in asking, of course. I'm going to put the YouTube channel at this point here. Okay. So, I'm going to share this screen. Okay. Good. Now, where are we? I'm going to enlarge a little bit the captions. I think this is good. So where are we? As usual, we can go to the /data/tutorial/tutorial samples folder, where I have put the information, all the necessary files for this tutorial. Of course, you can also find them on the GitHub page. Okay, so let's go to our corresponding directories. Now I am on for Spectra. So the first part of what we are going to do is we are going to compute the absorption spectrum of a single geometry. Okay, so let's go to the one lower bar ensemble folder. there you will find all the files that are necessary for that. Now, there are several files here, so in case you kind of get lost or whatever, you can still refer to the architecture of the tutorial that is on page 3 on page 4, sorry, of the PDF that I sent to you. So right now we are here, okay, 1/ensemble. So the tutorial is subdivided in 2 parts. So the first part is going to be the computation of that absorption spectrum, accounting either for both for a single geometry and accounting for sampling. The second part is going to be slightly different, and if we have time, which I hope we will, what we're going to do here is we're going to take one of those geometries and we are going to gradually increase the size of the QM region to see what happens with the excitation energies. There is an important point that I have to say. In practice, the accurate computations of excitation energies are all but cheap. So what we're going to do here today is we're going to use a semi-empirical method. It is called STDA. So we are kind of do so-called time-dependent DFT, but this is a semi-empirical approximation. This has also been implemented by Stefan Gremier, the same person who developed the XTD software. We are going to use Orca, so Orca has it implemented inside there. So as they are semi-empirical, they are rather cheap, okay? So of course, don't expect obtaining the exact same beautiful spectrum that I showed you before. But it will make the idea. Okay, so yeah, first part, ensemble. Here we're going to have the QM region, which is just going to be the azobenzene molecule. In the second part, we will have azobenzene, but we will gradually include more and more water molecules in the QM region and see what happens. So this has to do with a question that was asked the other day, in that how do you somehow include a solvation shell within your QM region? So we're going to use mobile tools today, and we will see how to do that. Okay, so we are now here on 1-ensemble. Okay, so the first thing will be
Gustavo, there is a
sorry?
question in the chat.
Oh, thank you. Could you please say why you have chosen this specific empirical method? That is a good question. Honestly, for no reason at all. No, I'm just kidding. Of course, there is a reason. The main reason why I chose a semi-empirical method is that, well, in order to make the computations feasible within today, so perhaps your question was more targeted towards why should we choose a method rather than a different one. It depends. It mainly depends on the degree of accuracy that you want to obtain. That's the usual problem. Accuracy, the ratio between the accuracy and the computational time you can afford. Of course, yeah, using this empirical method to obtain computations in like in research, well, referees would immediately ask you, but why didn't you use TD-DFT, for example, the actual time-dependent DFT without the semi-empirical approximation? So basically, it just, instead of computing some integrals, what it does is it puts some constants, some parameters, and replaces those integrals. I don't know the full details of the implementation, but yeah, again, you have to see what is the degree of accuracy, what agreement do you want to get with your experiment, and of course, you usually need to do benchmark with different methodologies. So already in density functional theory, you have to choose a functional which best reproduces the experiment. And then when you perform more than one computation with that function, you stick to it to be consistent. Otherwise, if you want to get some more accurate stuff, you do a complete active space, SCF with perturbation theory, or several other stuff that you can do. So yeah. Okay. Now let's begin. So what do we have here? Well, here we have the two necessary ingredients are the this guy here, the prod.crd, which is the trajectory that we ran the other day with azobenzene, and the parameter file. So yeah, let's just take a look at the system just to remember it. So we can open it with VMD. Okay, I cannot open it with VMD for some reason. Sorry about that. I will enlarge this thing here. VMD, yeah, I don't have it on the path. Okay, here it is. So we go to new molecule, then browse, then we open first the parameter file, and then we open the trajectory file with periodic box, because this is a molecular dynamic simulation with periodic boundary conditions. Okay, so well, this is the guy. This is actually the thing that you also obtained the other day. Let's, for the sake of visualization, expand this thing here. And graphics representations. So what am I doing here? Sorry. So I'm going to graphics, then to representations. I think we have already done this before. So I want to put a different representation for the azobenzene. Okay, because it's just line, but I would like to distinguish it from the rest of the molecules, which are water molecules. Okay, so let's click create representation and use the syntax to choose a representation we're interested in. So res ID, the index of our residue, I think it is 1. Let's change the drawing method here from lines to licorice. So I know I'm being repetitive because you have already done so, but it's just to remind you how to do this, because later we're gonna visualize a single snapshot and we're gonna see how the quantum mechanical region is increasing to see which water molecules are we considering in the region. But this is gonna be part 2. Okay, so this is the guy. Here, let us see how many snapshots do we have. So let's go back to the main. We have 200 snapshots. In order for us to make, of course, the computations within a decent time, we're gonna perform only 10 single point computations. In practice, 10 is a very small number. Sorry. So you should go to the order of hundreds of geometries to get a statistically significant, let's say, ensemble. But of course, I'm doing this just for the sake of time, saving time, of course, but also to show you what I want to show you later on. Okay, so we know the guy. We can exit. And at this point, so we have the trajectory. We want to generate a certain number of snapshots, of input files for different snapshots. Okay, so we're going to use, as last time, the mobile tools main script, which is main qminputs.py. Remember that whenever you want to visualize how to use it, you can put the option -h, and it is going to print this guy here. So it will, this thing here. So it will show you that you will need 2 input files: the main input file, which has general information, and the template, which contains specific information for for the quantum mechanical software you're using. So of course, we're going to use Orca today. Let us take a look at the main input files. So we open it with main. It's going to be pretty much the same as last lecture. So TPL, so the template is going to be an Orca template. So we have to specify which software do we want to use. Here is the topology file. So the file containing the parameters. Here is the trajectory file. The mask. So the mask we're going to put on the QM region exclusively the first molecule for the time being. And these are the geometries we're gonna take. So geometries from 0 to 9. At this point, in reality, you can choose whatever range you want, or you can stick with those. It doesn't matter. Of course, remember that if you have a long, so the nanosecond time scale molecular dynamic simulation, you will need to equilibrate the system, which basically means to attain a more or less constant average energy throughout time, which means you will get rid of the first, let's say, nanosecond or the first 10 nanoseconds of your simulation. So to obtain, let's call them just good results, we need long molecular dynamics trajectories. Increase the font size. Sure. Just one sec. I like this in here. Let's see if this improves something a little. Oh, sorry. I'm doing it the wrong way. Okay, here it is. Is that better? Welcome. Okay, so again, this is the, yeah, you were totally right. I couldn't see anything either. Okay, so yeah, this is the input. Pretty straightforward. Look at this guy here. What's going on here? Why isn't this guy called the prod.crd? Could somebody tell me what do we have to do prior to generating the input? I will give you a hint. I'll open again the trajectory. Just so remember that no, I'm not gonna say it because otherwise I would be saying everything. So I'm opening again the trajectory just to visualize what's going on here. So okay, so remember the trajectory is called the prod.crd. Okay, now look at the trajectory. What is doing? So where did we start? So basically, it's kind of, we started with a more or less compact thing, okay? Then this thing started to expand. Now, of course, this is a problem of the way, okay, there's a question I'll answer in just a second, of the way Amber is printing the output, because although we have periodic boundary conditions in the output file printed, it is not accounting for these periodic boundary conditions. This is just a format thing, in a sense that it is just printing the absolute position of the atoms. But of course, we have PBCs, and this means that we have one box, then it's replication on all 3 dimensions. Now, this is also something I said the other day, but I didn't put the visualization stuff. So basically, what we need is to image everything to the primitive solvation. So, sorry, to the primitive cell of the periodic boundary conditions. Okay, so we will have, as usual, to image our trajectory, and we're going to use CPP trash as usual. Now, there is a question here. From Danilo, how many trajectories are needed to obtain a good absorption spectrum? Is it possible to select the best snapshots in the ensemble? I mean, how can we obtain a good accuracy with a small number of configurations? Maybe some autocorrelation function could be used for this purpose. Yes. I mean, Of course, you could do some kind of clustering analysis. The important thing here is, I mean, if you simply take the snapshots completely in a random manner from your trajectory, you expect that they distribute somehow. So they are gonna distribute like with a I don't want to say it badly, but you're in equilibrium, so it should be a Boltzmann distribution. So of course, so you're going to take some of these snapshots with a larger frequency than, I mean, not the exact same snapshots, but configuration. Let's call them configurations. Okay, so you're going to sample some configurations with a larger frequency than other configurations. Okay, so if you just sample in a random manner, you expect that the distribution that you obtain be Boltzmann. Now, of course, you can do some clustering again prior to computing the actual spectrum, and you can see which are the more frequent ones, which are the less frequent ones, and on the basis of that, you take like the most representative configurations depending on this clustering analysis. So yeah, you can make the computation cheaper in that sense. I do not do that. I usually just sample randomly from my trajectory. And okay, so yeah, Juanjo has put a link on doing clustering analysis, which was the thing that I cited. So yeah, you can take a look at how to do that. I personally don't do that. But yeah, this of course helps you save computational time. Okay, so
Gustavo, yeah, maybe just one comment. These clustering analyses are usually done when for larger systems like proteins or things like that, where you have strong conformational changes. So let's say along dynamics, you have a protein which change a lot the structure. So you can analyze which are the 5 or 6 more representative structures. As you said, this is a clustering analysis. And then you just choose these 5 or 6 structures for the calculations. This is good for proteins because they clearly change conformation sometimes. But for small chromophores, I think this will not happen. Maybe for a chromophore, like a nucleobase, all the snapshots will belong to the same cluster. So at the end, you will have only one representative structure. So probably for small chromophores, yeah, it's better to take into account like 100 or 200 snapshots randomly chosen, probably. Yeah.
Great. Yeah. Thanks, Juanjo. Indeed, that's a quite important point. Okay. So at this point, yeah, we saw the main file. Let's take a look now at the template. So this is the template for the Orca inputs that we're going to generate. So it has, well, this first 3 things, which are the header. So the main information that Orca requires here, I called it header, but this need not be at the top of the file. This is where you define the methodology you want to use for the QMMN computations. So in this time, we're not going to use XTB. We're gonna do some actual density functional theory computations. So this is the PD functional, and the basis set, which we now explicitly define here, is the depth2 SVP. So it's a double Z with polarization. It's actually the standard basis set for, I mean, the default basis set for Orca in case you do not specify anything. We are requiring that it consider external point charges, the charge on the spin 0, 1. And there is this new section. It is called, well, TD-DFT, because we're going to do some time-dependent density functional theory. Notice that this syntax is pretty much the same syntax that you will actually find on an Orca input. So we will take a look at one of the inputs generated. Now, in this case, we're not really doing TD-DFT. We're going to use this semi-empirical approach, STDA. I don't remember what the S stands for. I'm sorry about that. I think I put the link in the and the GitHub Smart Swift. I don't know. I'm sorry. But yeah, it's fast. Maybe it's German, schnell. I don't know. So yeah, the important thing is that we are using this mode here, and we are gonna put a threshold. So what does this threshold do? So whenever you perform a calculation for excited states, I mean, I'm not gonna get into the details, but basically you have to specify which excited states are you gonna compute, and these excited states need to be ordered. No, yeah, the TDA, yeah, sorry, the TDA stands for Tam-Dankov approximation, which is already an approximation that is used in TD-DFT. So yeah, but this is great. This is Tam-Dankov approximation, but this S is the semi. I think the S stands for semi-empirical. Yeah. So when you compute, whenever you compute excited states, you need a range of excited states. Yeah, because you're diagonalizing a matrix, you're gonna get the eigenvalues and the eigenvectors from that matrix. So you can do that by obtaining that them with you obtain them in increasingly sequential order. The important thing is that you need to put a threshold. Now the threshold is not the number of states; it instead is an energy threshold, which means we are telling the program to compute all the excited states that are below 5 electron volts of difference from the ground state. So remember that for each excitation, you need an energy input. So we're computing excitations that require energy inputs below 5 electron volts. So this is measured in electron volts, okay? Okay. But then again, this syntax is specific for this STDA. For time-dependent DFT, there is a different keyword, which is, I think, max root, in which case you do define the maximum state you want to attain. Okay. So we have the main input. At this point, let us get the inputs, right? So let's call the main QM inputs.py minus I, just the main. Sorry, of course. I'm missing a very important thing. And I made a lot of emphasis in that, but I missed that point. What do we have to do before generating the inputs? We have to image the trajectory. Okay, so we have this prod.crd. In any case, if you execute it, it will give you an error because we do not have the trajectory file. So let us image the trajectory to the first primitive cell. So let's call cpp trash. Now let's call the parameters. So prod. Sorry, the parameter is system.param7. Okay, then trajin gonna be prod.crd. Okay, then traj out. Sorry, before the traj out, of course, the auto image. Then we put the mask we want to center our system on. The mask is gonna be the first residue, so 2 points, yeah, column 1, 2 points, whatever. Traj out. We called it imaged.crd. Okay, then go. So it's going to print that image.crd there, then quit. Okay, now we have our trajectory imaged. Okay, at this point, let's execute the main QM input. Minus I. This is the main input file. Minus T, the template. So we're going to generate up to 9 inputs from the first snapshot up to the 9th one. But again, you can define the range however you want. Okay, let's do this. So it's going to print all these things on the screen. So it means that it has generated the input for the corresponding snapshot. If you want to get this output in a file, you simply execute the same thing, and then use the greater than stuff and put the output .temp, for example. But yeah, this is not so important because there are no errors. It says everything went fine. This normal termination message here. Okay, now if we take a look at our folder, or the contents of our folder, we see that we have 10 of these folders. So let us access, for example, the geometry 0 folder. Okay, let's see what we got here. We have two files, just as in the previous case. So we have the file containing the point charges, which is charges geom0, and the file containing the actual input. Just for completeness, we can take a look at the input. The input for geometry 0, okay? Okay. Okay, yeah. The thing here is, I think it actually centered the box at the center of, yeah. Okay. So yeah, we have the again the header, the thing that I call the header, then the coordinates, and then it is also calling the point charges here with this command, the point charges command, and finally the time-dependent DFT command, which is here. So this is an actual Orca input. So this is the syntax, the correct syntax you would use for Orca. Okay, so how do we execute this? Of course, we just submitted the job for each one of the geometries, so we can do Orca if we have it on our path, which we should. Then geom0.int greater than geom0.int, let's call it .out, and we can put the ampersand if we want, but it is gonna take like a few seconds, so we can just execute it and see what happens. So of course we will have to do the same thing for each one of these guys here, so 10 times, but of course we are not gonna do that manually. Okay, it's like more than 20 seconds perhaps. Let's take a look at enlarge this on top. Okay, I see we are executing it here. Okay, it finished. So let's take a look at the output. Hopefully it did what it had to do. geom0.int.out. So this here is the Orca thing. We can directly go to the end of the file to see whether we had a normal termination. We did. It was really fast. In fact, most of this computational time was actually the computation of the ground state. So the normal density functional theory computation. The semi-empirical computation for the excited states was extremely fast. Okay, so now we go upwards a little bit more until we find this line here. Okay, so this is the absorption spectrum via transition electric dipole moment. Okay, so this is going to be the spectrum we're going to be interested in. So the first thing you're going to see, well, you're going to see a lot of things. But of course, yeah, this is the guy that we need to plot the spectrum, because the spectrum is, of course, so yeah, a set of geometries and the corresponding intensities. Well, here they are the oscillator strengths, which have a specific definition. I will not cover this. Just important thing here is that we need the energies. Now you can see that the energies are represented in two different energy units. So centimeter to the -1, which is the usual unit for example, IR spectra, or the nanometer unit, which is more often used in electronic absorption spectra, which is our case. Okay. So we're going to take each one of these transitions. So we have, oh, by the way, the states here are of course labeled from 0 onwards, but these states indicate that this is the first excited state, the second excited state, and all these states are going to be singlets. So where the ground state of the system is a singlet. You remember the multiplicity we put was 1. So here we requested that it compute the excitations towards singlets, okay? Because these are the excitations that are going to give non-zero oscillator strength. So these are those that are going to actually represent the absorption spectrum. Okay, so if we wanted to plot this thing, we would need to take this column, then this column, then put it on a file, an XY file or whatever, and then plot it however we want. Okay, so let's do this. So let's go backwards. And here we have, so we're not going to do it manually. Of course, you don't do that thing manually, especially when you will have to do with several different configurations. So you will most likely write yourself a script to fetch all these excitations and put them in a single file and then plot it whenever you want. So what we're going to do is we're going to use this script that I've put here, which is called plot spectrum. Guess what it does? Yes, it plots the spectrum. This is a Python script. This is a really important thing. Sorry, I didn't say it before, but I put it on the GitHub page. So we are going to use 2 more libraries from Python, which are called the matplotlib library, which is, let's call it the standard library for plotting, and this tk-inter something. But of course, I mean, you can also use, I mean, whenever you want. If you want to repeat the tutorial, you can also do it with whatever program you're most acquainted with. We're just going to use these things because I wanted to show how this broadening process works and what do we see, and so on and so forth. So if you have an Anaconda, of course, you don't need to install these 2 libraries. Okay, let's go back. So we will execute this script as follows. So Python 3, we call Python. Then we call this plot spectrum. Let us first use the -h option to see what does it do. So sorry, what does it do? We know what it does, but how to do that. So it takes as input the range of geometries we want to analyze. Now we have computed only one geometry, the geom 0. Hence, we're going to plot the spectrum for that geometry. Okay. Now the units we're going to use. The default is going to be electron volt. Now we have seen that the spectrum is going to be in nanometers. I mean, it was plotted in nanometers. Sorry, not plotted, but the output was with this unit. But you can choose either electron volts or nanometers. Also, the maximum state to consider. So as we saw, there were up to 13 excited states. The problem here, this is a very important problem, is that when you have an ensemble of geometries and this is particular for the method we're using. So remember that we're putting a threshold in energy. It means that as the excitation energies for different geometries need not be the same, because otherwise we wouldn't have any broadening. It might be the case that in one geometry, we're going to have, like, I don't know, 11 excited states, whereas in the other one, we're going to have 13 excited states. So let's put a small number so that we are sure that we consider all excited states for all geometries. So default is going to be 5. We're just going to use the default. And this thing, what it does is it colors the bars by state. Okay. Default is false, but we want to color them for seeing what's going on here. Okay. So F, we only have one output. So let's put 0, which stands for geometry 0. And minus CB, let's put true with uppercase T. Hopefully it will do what it has to do. Sorry. Okay, so this is what you will obtain in your screen. Of course, yeah, this is a graphical user interface, so you should have connected with minus X. If you are in our cluster, of course. Okay, so what do you see here? Well, you see we're considering up to the 5th excited state. Let's enlarge this thing a little bit. You can better see it. Okay, so we chose energies in electron volts, but it doesn't matter. We could have just as well have chosen nanometers. Yeah, we have the first excited state that is centered here, and so on and so forth up to the 5th excited state. So this is what people often do, except that we take the equilibrium geometry because it's more correct, like the average geometry if you're around the minimum. And then we put on top of it some broadening, okay? So we can put, you can use different functions. In this case, we use Gaussian functions to broaden each one of these guys here. So we have to choose like the width. It's actually called the full width at half maximum. So we can put, for example, 0.5 electron volts. It is in electron volts because we have the energies in electron volts. Okay, so here's the spectrum. With a single geometry. You can compare it now. If you have computed the spectrum with a really accurate method, I don't know, CAS-PT2 with an extremely large active space and a lot of roots, then this thing will most likely resemble the experimental spectrum, which is good, of course. But again, this broadening is non-physical. Okay, so this is for one geometry. Of course, whenever you write your papers and do this, you will have to report the full width of half maximum you have used. Okay, let us exit. And well, at this point, what do we have to do? We have to compute the spectrum for our ensemble of geometries. This is the main goal of this part. Okay, so I think I have prepared a submission script that is inside here. It's called submit.sh. It's just a for loop, so it is going to iterate over each one of the geometry folders and submit each one of the calculations. Okay, I guess we can at this point. I mean, this is going to take overall like between 3 and 5 minutes. As usual, we might do a pause now. I mean, we of course first submit the calculations, then we can make a break if you want. Today's tutorial is not going to be too long, so this pause could be shorter. Or yeah, if you prefer. Otherwise, we can go ahead until the end. What would you prefer to do?
Let's have a coffee.
Let's have a coffee. That's a good thing.
Coffee and bocadillo, and after that, un merengue.
Un merengue, of course. That's an excellent idea. Okay, yeah, then then let's do this. Let's submit the calculation. We can do it with no hub. Then /submit, then ampersand, and it is gonna execute in background. Okay. We do a top. We have that already. Some of us are running it, and yeah, we can make a break and see you in 10 minutes.
Yes, yes.
Okay, stop sharing. this lifespan. Okay, Okay. Hello. Okay, so let's see. There are some questions. Okay, by the way, what is the name of your Linux? Okay. Yeah, I'll just wait for a few minutes until people arrive, I think. The other one, anyone else had an error in the very beginning when running? Okay, I'm gonna answer to Amin. So the Linux distribution, so the one I'm showing here is, I mean, the same as that, the one that you're using in our cluster, it is CentOS 7. But of course, if you're asking for the one in my laptop, the one that I used the other day, was simply Ubuntu 20.0, I guess. But of course, this is the Windows subsystem in Linux. So I actually have Windows and have the Ubuntu application inside. Jocelyn, could you solve the problem in the end?
Yes, it was my mistake. I forgot to one letter was wrong and I didn't see.
Okay, great. Cool. There's one that is still running, I suppose. So if everything went smoothly, you can see whether it finished by taking a look directly at the at the output inside the geom9 folder or whatever was your last geometry. Okay, so I'm gonna share the screen again. Just let me all know in case you were already online. Give me a signal. But I think we're all here, maybe. Okay, I will share the screen. Okay, here you go. Okay. Okay, so did all of your calculations finish properly? How can you see them? Again, I went to the geom9 folder and saw that there was this file here, geom9.imp.out. Yeah, of course, we went to the end, and you can see that there is a normal termination there. So did you have any issues with the submissions script or with the generation of the inputs or whatever? Chat. Okay. Yeah. Awesome. Great. Then I think I will assume everything went smoothly. So yeah, we're still in part one. in the sense that we have computed the absorption spectrum for a single geometry. And now what we're going to do is we will use all these outputs that we got to construct our absorption spectrum. So remember, we don't have 10 geometries here, but it will suffice to see at least what we want to see. Just to recap, let us plot once more the spectrum with only one geometry. It doesn't matter whether it is 0 or whatever. So again, Python 3, then plot spectrum. I don't remember where are all the arguments. So again, so plot spectrum, so -f, 0, then -cb, let's put true, and the other arguments are going to be the default arguments, which are shown here. So okay, this is what you obtain from a single spectrum, from a single geometry. So you have the 5 excitations here. Okay, let us see what happens when we instead use an ensemble of geometries. In this case, there are going to be just 10 geometries. We're going to have 5 excitations for each one of the geometries, which means overall we will have more or less 50 bars here. So let's do it. Okay. Yeah, please ignore these things here. These were just for debugging. I forgot to remove them. Okay, so again, we can just look for the command that we executed. Now, remember that the first argument is going to be f, which is the range, the geometries. The f stands for file, but yeah, of course, it refers to the range of geometry. So we're going to put 0, 9, just separated by a space, so that it takes the whole range of geometries. And CB true, and yeah, that's it. So let's do it. There you go. So this is exactly what we wanted to see. Now I have done a thing here in regard with the colors of the bars. So the colors here, what are they indicating? They indicate let's say each one of the states. So let me be a little bit more clear. So for example, we have these bars here. So each one of these bars will correspond to a specific geometry, and it's going to be, let's say, formally the S1, okay, for each one of the geometries. Now, in practice, and this is something really important, in practice, see what happens, for example, in this region here. I hope the colors are not too problematic. Now, see that, for example, for some geometry, the thing that I call the S2 is way ahead than the S3 of some other geometries, and also even with some S4s. This means that for some geometries, you might have the shifting in the states. What does it mean? For example, for geometry 0, suppose that the S1 was this one and the S2 was, I don't know, this guy here. For a different geometry, the S2 might be this guy here, which is above the S3 of geometry 0. So the coloring here does not indicate that all these bars here are necessarily corresponding to the same excited state. Now, what do I mean with the same excited state? I mean the character, okay? So the really important thing here is, well, we obtain the broadening from the spectrum. Also, the labeling here is not so important as the character of the excited state. Okay, so once again, we have our spectrum. We can still apply some broadening in order for us to compare it with the experiment. What the broadening is going to do is simply it will just add up Gaussians centered at each one of the bars. So let's put, for example, 0.3 electron volts, and we get something like this. Okay, so this is going to be the absorption spectrum for azobenzene, considering up to the 5th excited state. Yeah, now this, of course, well, here we have the energy in electron volts, but we can also do the same thing, but with nanometers, so that we can even better compare it with the experiment that I have reported at the beginning of the tutorial. I guess we can do this in a single line. So we exit and we execute this thing again. But now we also put the argument minus. I always forget these things. I put the names and then forget them. Sorry about that. Okay, so it is units minus U. Let's put nanometers and see what we get from this. Okay, so as you can see, first of all, the electron volts and the nanometers are inversely proportional to one another. This means that now the higher energy excited states appear to the leftmost part, and the lower excited states appear to the rightmost part. Okay, let's put the broadening again. This time, however, we have nanometers, so we should be consistent with the size, with the width here. So, for example, 10 nanometers. That's where we get. This is a little bit small. Let's put 50. Okay, yeah. This is a better broadening, so you can more evenly see each one of the bands of the spectrum. Okay. Does it look like the one from the experiment? Let's see. Now, did I download the presentation? No, I think I didn't. Okay, so I'll just download the presentation from the GitHub. It is here. Slides. So here it is. So okay, we have in principle I think we had the trans species. So we had one band at 450-ish, 500 nanometers, and the second band around here between 300 and 400. Now what we see here, is it similar? Let's put this here. Let's put this guy here. Yeah, of course, we see 3 bands. We also see these 2 guys here. I think they might be outliers, or in the sense that they might be geometries that are strange distortions, something like that. But yeah, of course, the absolute energies do not properly agree with the experiment. So if these were the first band, which should be its center at 600 nanometers, we're way too off with respect to the experiment. But yeah, hey, this is the best thing we can do. This depends, of course, on the methodology that you use. I don't even know whether that depends on the functional that we used or on the semi-empirical method. I think this is more related with the functional that I chose, which was the PDB functional. So this is what I meant at the beginning with doing benchmark. So you have to benchmark functionals, try different density functional theory functionals, so that you get the best agreement with the experiment. Okay, so yeah, we have the three bands, 1, 2, 3, kind of. Yeah, the energies are not correct. So this is it. This is, I mean, the basics on how to get the absorption spectrum with a species, considering sampling. Sorry. Okay. One last thing before we go to the second part. I think we will. In case, I think we'll finish within half an hour or so. But yeah, I wanted to take a look at another thing. So let's go to, for example, geometry 9, because why not? Let's take a look at the output again. So geom9.int.out. Okay. So I was at the end of the file. Let's go a little bit upwards. So yeah, this is perhaps you remember this string here. This is the energy of the ground state. And of course, each one of these transitions, what are called transition energies here, the transitions are basically the energy differences between this ground state energy and the energies, the absolute energy of each one of the excited states. Of course, this number here, final single point energy, is represented in Hartrees, which is an extremely large energy unit, let's say. But when you compute differences, you obtain these values here. So these are 600 nanometers, which are 0.001 Hartrees, perhaps even less. So yeah, just to say that these things here are energy differences, and this is what we usually measure in chemistry. Now, okay, another thing I wanted to point out before we move to the next section without getting too much into the details. So I went a little bit upwards and I came to this section here. In reality, it doesn't matter what software you use to do time-dependent DFT. You will most likely have these things that are represented, for example, here. So there is a number, then an arrow, and then another number. So these two numbers usually represent the orbital. So I think most of you are acquainted with at least the atomic model and the electronic configurations and how you obtain electronic configurations for molecules. Okay, so in each electronic configuration of a molecule, you have orbitals, and each one of these orbitals is occupied by 2 electrons. So this is the really intuitive way of thinking about the electronic structure of a molecule. Really, really intuitive. But yeah, what is shown here is basically what is the now, okay, in this line, we're analyzing the first excited state, okay? Or rather, the transition from the ground state to the excited state. So basically what this line says, especially this part here, so it says that one electron departs from the orbital number 21, which I assume will be the HOMO, the highest occupied molecular orbital, and will go towards the orbital 22, which I will assume to be the first unoccupied orbital. Okay, so this electronic transition from a qualitative point of view has this character. So one electron leaves the HOMO and goes to the LUMO. Of course, these transitions are, the electronic transitions are far more complicated than that one electron picture, but because you also will have, let's say, contributions from other, let's call them excitations, but this is beyond the scope of this qualitative discussion. So yeah, each electronic transition, each transition formally can be, in a more qualitative manner, be represented as the jump of an electron from one occupied orbital to a virtual orbital. And what does define the character of the transition? Because I mentioned this before, I mentioned the character. The character of the transition is going to be determined by the nature of these orbitals. So perhaps you have heard of pi orbitals, pi star orbitals. So what's the shape of, let's call it the electron density. So yeah, the orbitals define kind of how bonds are formed and so on and so forth. Of course, orbitals are actually functions, so are not, let's say, real things. But yeah, so the character of the transition is defined by the nature of the orbitals that participate in that transition. So does it involve like the aromatic system of benzene, or does it involve an orbital which is present in a bond between two carbon atoms. Well, this is what defines the nature of the orbitals. Okay. Yeah, so this is also relevant information when you compute absorption spectra. You will characterize each one of the states that you consider. You not only do that plot, but also characterize the states. Okay. Okay, I'm not being able to close this thing. Let's see whether there are questions. Not so far. So at this point, we can go to the second part of the tutorial. And here we will deal with what's this guy here? Yeah, okay. So we'll go to this QM size folder. And as I said before, what we will do here is we will take a specific geometry, could be anyone. We will take the geometry number 6, because yeah, we have some scripts that do this automatically, and I chose the number 6, but you can change it from within the script if you want. So what are we going to do here? We're going to take our system, we're going to prepare 5 or 6 input files, and we are going to gradually increase the number of molecules within the QM region, but of course considering the exact same geometry, because we want to see how do the excitation energies, that is the energy differences, scale, or how do they behave as we increase the size of the QM region. Now, this is perhaps an analysis that is not so significant in the way, at least we're going to do it here, for excitation energies, because there are more complicated factors in that. So for example, if you put more molecules in your QM region, those molecules could also participate to the excitations. But we will see it nonetheless, just to see how do we see the scaling of quantity with increasing the size of the QM region. So remember, in this case, we had just the azobenzene molecule in the quantum mechanical region and the water molecules in the anion region. Here, we're going to take from 1 up to 5 water molecules in the QM region. So let's do it. So let's go to minus, minus, minus. So we are here. So let's go to the 2QM size folder. And there you will, well, of course, you will find the exact same files that are reported in the manuscript. So there are 2 important things. Again, we're going to use MobileTools to generate the inputs. So the 2 input files are here, the template and the main. The template is going to be the exact same one as before, so nothing is going to change. So I will not open it again. I will open the main input file because something will change here. Remember, the main is the one that contains the general information of the inputs we want to generate. So it apart from this thing here, it is independent of the QM software you want to use. So these lines here are the same as before. Okay, so we're going to use Orca. We will give this as the topology, this as the coordinates, and the QM mask will still be the azobenzene molecule for the time being. The geometries, we will choose geometry number 6 from our trajectory. You can choose whatever geometry you want, but you will also have to change consistently these numbers in this analysis scripts that I also provided. Okay, so 2 things. These are the 2 new keywords added here. The first one is called solve mask. And remember, so this package is built, let's say, on top of CPP trash and PyTrash, in the sense that it uses CPP trash to do some operations here. So I'm trying to use the same syntax as they somehow use. Of course, PyTorch is not mine. It's part of Amber Tools. So every time you download Amber Tools, you already have TD-DFT on PyTorch. So the solve mask, what it does is basically it defines a specific residue, or well, not a specific residue, but whatever you put here as a solvent. So for example, if you had a system consisting of solid water molecules, you tell it, okay, my solvent is going to be water, and of course the name of the residue is what, the TIP3P solvation model. But if you had a more complicated system, for example, a mixture of water and something else, I don't know, acetonitrile, why not? Then you should put both of these molecules here. Although that specific situation is a little bit more complicated to deal with. But yeah, so here you define a solvent. So the solvent is going to be the environment, the thing that surrounds your solute, obviously. And in our case, it's going to be water. So why do we do that? Because afterwards, we want to grab the n closest molecules to our QM mask. Okay, so if I say closest equals 1 here, this means that it will also include the closest water molecule to my solute within this snapshot. Okay, so this is something that we talked about the other day, in the sense that what happens when you include also solvent molecules in the environment. Now, of course, we're performing single point calculations, so it's not going to be a problem in the sense that if we just choose the n closest molecules, you have to do it throughout the trajectory to be consistent. If you do QM, MM, MD, the situation is slightly different. It's like more complicated. One last thing, of course, what we want to do here is to see the scaling. So we're going to vary this closest number here. So we're going to generate an input for azobenzene plus 1 water molecule, an input for azobenzene plus 2 water molecules, and so on and so forth. Okay, so this means we would need more than one input here, more than one main dot input. Okay, so I've prepared a script to generate the inputs. It is called gen inputs. But perhaps before we do that, let's first copy the ingredients we need to get the inputs, obviously. What are these ingredients? Well, the topology file and a coordinate file. So we're going to copy them from the other folder. So let's do a cp --/1 ensemble, and this guy was called the system.prom7, so we'll put it here. And the same thing for the trajectory. So of course the trajectory we're going to use is the imaged one. Okay, so image.crd, let's have it here. And yes, now for the time being, let us generate the input file for the first case. So the case in which we include 1 water molecule. So the main is the input is this guy here. We have closest equals 1, and the template is this guy here. So the template is the exact same template as before. I haven't changed anything. Okay, so let's do it. Main QM input. So the syntax is the same: -I main -T TPL. Let's see what happens. Something that might be relevant for some of you eventually is that at this point, well, the execution of the script is printing something that might be important, perhaps, because perhaps you want to know it for some reason. It prints the residues in the QM region here. It always does so, but so far we have ignored it because we already knew that the residues in the QM region were just residue number 1. So in this case, it actually prints the index of the closest residue that we chose for that specific snapshot. So in the trajectory, it is going to be residue number 96. And of course, this is a water molecule. Okay. So that's why perhaps it would be useful to execute this this thing, creating an output file, so that you have a record of whatever it did. So yeah, we can do so. So out.dat, for example, that will create this. It didn't print anything because it printed it out on this out.dat. We can open it up. And yeah, you have the exact same information as before. Of course, yeah, you have the record of these guys here. If you had 2 residues, then it would print the labels, sorry, the indices of the 2 closest residues to the water molecule, to the azobenzene molecule. Okay, so let's make an ls to see what it did. It created a folder called geom6 because, of course, it always does so. So let's go to the geom6. And yeah, so you have the input file and the charges as usual. So nothing has changed with respect to what we would have expected to obtain. However, if we open it, now you will see that, well, yeah, all these lines, all these lines correspond to azobenzene. And there are now these 3 extra lines. What is this? Well, it's pretty obvious what is it. But this is the closest water molecule to azobenzene. Notice that now it is part of the QM region. And this will also mean that this water molecule will no longer be present in the charges file, because of course we have included it in the QM region. Therefore, the corresponding point charges that were here before in the previous calculations, they're no longer going to be there, because now these are quantum mechanical atoms. So their role has been changed. Okay, so now the problem here is that if we executed the main QM inputs every time changing the closest number, it will always create this geom6 folder and would override it, because this is the way the program is implemented. So that's the reason why I have done this gen inputs.sh script. We'll execute it in a second. It's awful, but it does its job. So what does it do? So basically, it will create. We're going to iterate here throughout the number of closest residues that we want to generate. Okay, so it will create 5 different folders, each containing the input that we want. But these folders are going to have a special name so that we recognize which folder corresponds to which input. So yeah, I will not go through all the details because I really don't like this syntax. So instead, let's just execute it and see what it does. So -- then inputs.sh. It shouldn't take that long. So we can just execute it that way. Yeah, of course, I did, let's say, the mistake that I did not put it in an output file. So we can also do that. Call it again out.dat, and we'll see what it prints. Okay. Please ignore these things that appear here. So cannot remove blah blah blah. This is unimportant. This will not influence anything at all. So first of all, let's see what it did. Let's see what it did. Okay, so it created all these folders: 1 res geom6, 2 res geom6, and so on and so forth until 5 res geom6. Perhaps you may have intuited what this 1 res 2 res means. It means that here we have one residue with residues in water molecules and 2 water molecules, 3 4, and 5. And of course, in each case, we will have a larger TM region. Okay, at this point, before launching the calculations, I know we all want to launch the calculations, but they're going to take so little that let's visualize things that are happening here. Okay. So of course I cannot visualize here, so I have to switch window. Okay, so let's open once again the VMD, the trajectory with VMD. Okay. So my system here. Yeah. Okay. So let us open the trajectory, new molecule, and browse. Same thing as before. First look for the parameter file, and load it, and then we'll look for the image trajectory with periodic box. Okay, so there it is. Now see first of all the azobenzene is at the center of the box, kind of. The important thing is that it is here and that we no longer have this expansion slash explosion that we saw before. This is big because we imaged all the molecules to the first sort of primitive cell, which we need to do single point QMMM computations. Okay, so for the time being, let's go to graphics, representations. Let us choose a representation for this molecule here. So for representation, let's select. This is the exact same thing that I did before. So res ID 1. And this will select the benzene. With VMD, we can rotate. We can also translate by pressing T. So I press the T key on my keyboard and then just moving it around. Then press R again to go back to rotation mode. Okay. So I did it just to better visualize the thing. Okay, so here is azobenzene in a different representation. I just did it to distinguish the QM region from the MM region in our previous calculation. This is what I did before. I'm going to do something else here. I'm going to change the display here on top. Change it from perspective to orthographic. So it no longer gives us this perspective visualization. I think we can better see it that way. What else? Yeah, okay. So now let us open, for example, the geometry of the first input. So if we go back to our terminal for just a second, well, I think you will have this thing executing, so I'll just do it on the screen. So you have all these folders have been generated by the being able to plug them. So here they are. Now there's also this folder that has been created before. In this folder there are these X, Y, Z lower bar res. We go there, we do LS. We will see the geometries of each one of the inputs. So this thing is done by this like naive script that I did, so that all these geometries be present in the same folder. This is just for the sake of visualization, because MobileTools does not generate an XYZ file, which is bad, and I will change it. But yeah, for the time being, we just have this thing. So what we're going to do is we're going to open a couple of these files. We're not going to open all of them, just so that you get the idea of how are we increasing the QM region. I know it's quite intuitive, but still it's best if we visualize, especially because, for example, if you needed to choose which one is the closest to our molecule, well, this is kind of difficult to do by simple visualization. So yeah, CPP trash does that in an awesome manner. So yeah, at this point, let's go to main. Oh, sorry. I think you can all see what I'm doing here. Yes. Let's go to file and let's open a new molecule. So you can open a brand new molecule in the same session that you are. Okay. The important thing is that in these load files you need to have the new molecule setting here. Okay, otherwise you're going to overwrite what you have here, because you see we already have this molecule loaded, but we need a brand new molecule. Molecule, of course, using the VMD jargon. It's not an actual molecule. Okay, so if we go to browse, go on top, let's go to this XYZ res and open the one res, sorry, geom6.xyz, and it recognizes immediately that it is a X and XYZ file. So let's load it. Yeah, of course you're gonna see this thing here that it's not in the same position. What the reason is because this is a specific geometry of the trajectory. Okay, it is geometry number 6. So this means that we have to look for geometry number 6 in our trajectory. So now let me see if I can do that. I think it kind of gets confused. So yeah, we have to go to geometry number 6 in our trajectory. So let us for the time being just remove this molecule, the one res geom6, so that we can now navigate through the snapshots of the initial trajectory. Okay, so let's put 6, and there it is. Okay, so this is geometry 6. This is from where we got our other geometries. And I'll do this thing faster. Now again, file, new molecule here, browse, and then one res geom6, then load. Okay, so now they're superimposed. Of course, we don't see it because of the representation of the other one. Let's go back to representations, and here you can select the molecule. So here I could go back to the initial trajectory, and I have my different representations. I can go to geom6.xyz. So this is the guy whose representation, and this is the guy that I want to visualize. So yeah, let's see what is this geometry made of. So let's just leave this as all, and change the drawing method from lines to, I don't know, bakeries. And well, of course, the isobenzene is going to be superimposed because it has to be that way. Otherwise, we will have different geometries. But the important thing is that now this guy here, this water molecule that was before represented as lines, oh, see, it is now represented that way. This is just a visualization thing. Please bear that in mind. We're just seeing which one of the molecules from the region we had chosen to create geometry 1. Okay, so it is this guy here. So this is the closest water molecule to our isobenzene molecule. Okay. We can do that with a second molecule, and then you will get the idea. So let's go to molecule type browser, load files for new molecule, and we browse. We load the second one. Let's load directly the 5th one already instead of doing the scaling. So we load it, and there it is again. Of course, we don't see anything until we change the representation for that geometry. So let's go to representations. If I'm going too fast, please let me know. I'm just doing the repetitive stuff. That's why I'm doing this stuff fast. If I'm going too slow, again, please let me know. But yeah, so we have selected here 5 res, and we go from lines to licorice, and voila. So these are the 5 molecules that are included in the region. Okay. Now, please notice that even though we include quantum mechanical, even though we include some part of the environment in the QM region, we still would need some kind of sampling. And the main reason is because this is just a single snapshot of a trajectory. But if we got a different snapshot, of course, we would have these water molecules placed somewhere else, and we would definitely have different excitation energies. So this sampling is important. That's the whole point of that is what I would like you to take home. Okay, so that's it. At this point, we can submit the calculations. Let's close this window. Yeah, so where are we? We are in XYZ res. So one step backwards. We have a submit script, which is pretty much the same script as before. You can open it, but it's the same script that, again, that we used before. I have only changed the name of the folders because now, of course, their names are different. It will take less, so yeah, there's no point, let's say, in doing a pause. So now hub dot slash submit dot sh ampersand and make it roll. Okay, so is it rolling? Yes, it is. Okay. So let's make an ls. So it is going to show the most recent file that here. Of course, currently it's running the one res geom6. So it will take again. Okay, yes, it will take a little bit more time for example, for this guy here, because we have more quantum mechanical atoms. But yeah, I did the benchmark, so it's going to be for this guy here, it's going to be like 1 minute, or at most 5 minutes for the entire set of computations. Okay, so let's see how's it going. So we're already at the second one. So yeah, again, if you have any questions, don't hesitate in asking. Please remember that in case, I mean, in case you wanted to redo these things at home, and if you had further questions in that regard, you can always write us an email, as some of you have already done. It's perfectly fine. So yes, another thing here is well, of course, some of the things that I would like you to take home is, remember, if you do classical molecular dynamics, you should perform simulations for rather long time scales if you can. Right? What I used to do is for this system is a little bit exaggerated, because these are rather small systems. You could run 100 nanoseconds of simulation, or even 50 nanoseconds, and you cut off the first 10 nanoseconds of the simulation. 50, 40, 30. Of course, the simulation time will be that you would need to have like converged, let's say, energy. Will depend on the size of the system. So yeah, of course, I run these 100 nanoseconds using like the GPU version, but again, if you have a small system, that may not be the time scale. So let's see how we're doing. I think it is almost done. So yeah, let's go to the 5res geom6 folder, GNLS LTR. It is going to show a lot of .tmp files, which indicate that these guys are temporary files. For our system is rather small. Okay, this is actually something really important if you're just working with quantum mechanics without sampling, without classical MD. These calculations could generate and actually do generate some temporary files which are rather heavy. These are mainly the 1 electron, 2 electron integral. So it is also important to if you're gonna run a massive amount of these calculations, you should be aware of the fact that these temporary files are going to be generated. They occupy, of course, hard drive space. So either you are submitting these, let's say, these computations to a supercomputer cluster, or in which case, yeah, hard drive, nobody cares, kind of. Otherwise, yeah, you should be aware of that and more or less measure the amount of hard drive at your disposal. So it is done. Okay, so we are in the 5res geom6 folder. The output is just called geom6.imp.out. It is going to be the same for all of the folders because the geometry is geom6, but it doesn't matter because we're in a different folder. There's nothing much different from what we had talked about before. We can open the output and see what happens. So we see what can we find. Yeah, well, this calculation took 1 minute, which is okay. I mean, of course, it's okay because of the level of theory we're using, and also because we have kind of a nice system, nice organic molecule. If we had a transition metal complex, things would be far more complicated. But yeah. Okay, so yeah, if we go upwards, notice one thing: the final single point energy. Perhaps you don't remember, but the one that corresponded to, I don't know, geometry 6 of just the azobenzene molecule in the QM region was about 500 and something hartrees. As I said before, I'd like to point this out again. We are increasing the size of the system, and this is the absolute energy. So of course, the more molecules you have in your quantum mechanical region, the higher the energy is going to be. Now, higher, of course, this is negative, so I should say the lower. But yeah, the higher its absolute value. Now, when we compute excitation energies, when we compute interaction energies, whatever we're interested in energy differences, and if the method is size extensive, then these things should converge at some point. Now, this is important, especially, for example, if you are having to do with interaction energies, which we didn't deal with here. But yeah, ground state properties. When we deal with excited state properties, things are far more complicated. So again, don't take these analyses that we're doing as something that has to be done like that thing, because of the thing that I talked about earlier. If you have more quantum mechanical molecules in your system, they might participate in the transitions, in the excitation, so the character of the excitation is going to be different. But nonetheless, let's just see how the first 5 excited state energy differences change. So let's go backwards to QQM size. And yeah, let's do these analysis. So there is yet another script. This is not going to be interactive as the previous ones. We will just generate an image that will contain the convergence of, well, I should say the lack of convergence, but yeah, of the energy differences as we increase the size of the QM region. Okay, so let's do it. So we execute it as Python 3 plot comparison.py. Yeah, it will do everything automatically. Of course, it is set so that it considers just up to 5 residues in geometry 6 and so on and so forth. It's going to do something like that. Then it will close immediately afterwards. However, it will have generated, sorry, this PNG file, which is an image. So if you're on Linux, you can just open it using the EOG program. Now, as I said before, this is CentOS. I think Ubuntu's distribution doesn't come with this EOG stuff. So instead, you can just copy it on your PC and open it up with the graphical user interface of your personal computer. So EOG comparison.png. Okay, so this is what it shows. Again, I have labeled them as S1, S2, S3, but this is somewhat arbitrary. So of course, for example, for the first, let's take a look at the S1. So okay, when you consider one water molecule, it's about 2.15 electron volts. Then when you go from 1 to 2 molecules, it's more or less the same. Then again the same. So we could in principle say that the S1 vertical energies are kind of converged. Problems arise here, as you can see, there is kind of a jump here, but this is mainly due to the fact that now we're having different excitation energies. They're kind of going lower in energy, but as I said before, the excitation energies are not a good example for showing this this convergence between region. A better quantity would be the interaction energy. It's something that I showed the other day in the presentation. But yeah, so one last thing. So yeah, of course, do not use this thing as a criterion for to determine a specific size of the QM region for absorption spectra. Now, if you had to do with one excited state, so for example, if you were performing calculations on the S1 and that's it, then this thing might work. But the problem is here, if you consider more than one excited state, you would have mixtures between different states, and things are far messier. But yeah, obviously it depends on what you want to do. And again, the computational cost that you want to attain or to avoid. Okay, with this, I think we are done with the tutorial. Again, if you have any questions, you can ask them now or later. We will always be available. And yeah, of course, well, I think we concluded the seminar series here. Yeah, thanks a lot for following us up to this point. Let's see.
Thank you, Gustavo.
I'm gonna stop sharing the screen for the time being. Okay.
Okay, so let's wait, let's say 1 minute or something to see if there are questions here or in the channel.
Mm-hmm.
Because the channel has always delay.
Yeah, that's fine.
Okay. So I think now people with these two tutorials, this one today and the last one from the previous day about redox potentials, I think maybe they will be able to run mobile tools, right?
Yeah, I think so. The main idea of doing this convergence stuff was simply to cover that feature as well, of including QM molecules in environment molecules in the QM region. But of course,
Yeah,
they can now do it autonomously.
We also have another tool for tracking the active space. That's very interesting too.
Yeah, it is also there in the mobile tools package. You can already make use of that. Yeah, I didn't cover it today because it's slightly more complicated, a little bit more technical. but of course, I think in the mobile tools manual, I think I put a part in some examples on how to use it. But yeah.
For the next season, you can talk about this.
Of course. Follow up.
Okay. So it looks like there is no questions.
Okay.
So maybe we can stop.
everybody, if you wish to talk something to ask, please open your microphone. It's easier.
I see that they're writing in the chat. Thanks to you, because yeah, you were here throughout the seminars until the end. And actually, I gotta say, I received both me and Vito received several questions, so also feedback from the students. This is from the people that follow the courses. This is really cool, very important. Of course, if you have further questions, again, we are available whenever you write us.
Okay, before saying goodbye to you guys, I will stop the YouTube session. One moment.
Yes.
So let's say goodbye to the
goodbye to
people in YouTube. Yeah, thank you for attending. Okay, before stopping, there is a question indeed. So Sabrin is asking if mobile tools can be connected with other tools external, different than Orca.
Yes. Yeah, the answer is yes. For the time being, there are interfaces for for Orca, for NWCam, Gaussian, and Molcas. Yeah. Molcas. It also does this, the active space stuff. So it also has Molcas there. But I will be putting more interfaces there. Of course, if you. Yeah, I'm also happy to hear that in case you needed something extra, I could also implement it. Actually, it's cool that people use it because we can get feedback from them, and so we can improve it. So
okay,
yeah.
Good. Okay, so now yes, I stop the YouTube session. So goodbye to everyone. Okay.